I will now present our work on guided sequential manipulation planning using a hierarchical policy. Task and motion planning can be used to solve sequential manipulation planning problems like the one you can see on the right. While this approach is generalizable, it lacks scalability for long horizon problems. Thus, we propose to train a hierarchical policy for high-level action selection, which acts as a heuristic and speeds up the search process. Then, we use a nonlinear program for the motion planning phase. More specifically, we solve a supervised learning problem, given a dataset where the input consists of the objective, which is a sequence of goals, and the state, and the output is the next high-level action. We want to find an input-output mapping such that the cross-entropy loss function is minimized. For this, we divide the high-level action such that it can be determined in 2 steps using a hierarchical policy. The high-level action is divided into an instruction type such as grasp and the symbols involved in the action, for example the grip I used and the box to be grasped. Both representations are one-hot encoded. The flow of our framework is as follows. The instruction policy determines the instruction type. Then the expert policy specifically trained for the selected instruction type determines the symbols. The high-level action then is converted into an NLP to be solved for the next configuration. We can then construct the next input for the hierarchical policy, and this process is repeated until the objective is satisfied. Then we can solve the NLP for the full optimal path. We evaluated the approach for generalizability in several pick-and-place experiments. The objective consisted of up to 2 goals. Above displays the keyframes of the path. These are the configurations after each selected high-level action only. Below you can see the full optimal path that is computed only after the objective is satisfied. We trained for 40 out of 72 objectives consisting of 2 goals and tested for both all and unseen objectives. As you can see, a solution is always found, and the shortest solution is found in over 90% of cases. When adapting the objective to consist of only unsatisfied goals, the performance is improved further. We also compared the scalability to a state-of-the-art task and motion planning framework, the LGP, for different problems that required a different number of high-level actions. Here you can see the solution of the proposed approach for the stacking of 3 boxes on a tray. For this problem, the proposed approach already requires significantly less time and expanded nodes to find a solution. Here you can see the solution for the stacking of 5 boxes on a tray. While this can be solved in feasible time by the proposed approach, the LGP framework fails to find a solution as the maximum tree size is reached. To sum it up, our proposed hierarchical policy improves the scalability while ensuring that the shortest solution is found in a majority of cases. Next, by evaluating our framework on different tasks, we aim to demonstrate the effectiveness of these domain-specific heuristics for long-horizon task and motion planning problems.